So today we're going to kind of continue along in this chapter 3. So we're going to do kind of more special techniques. And generally, the idea between that we talked about last time and that we're going to do today is to be able to find the potential. We want to be able to find V, and for the most part, we were trying to avoid doing direct integration. Because anytime we can avoid doing some integrals, that's a sort of a happy day. So we have, V, if we were just trying to do it kind of by hand, we would have to take an integral and add up all the little bits of potential due to little bits of charge dq and add them all up basically. And on paper, that doesn't seem that bad. That doesn't look like a terrible integral. But as soon as you start getting kind of, strange shapes or different sort of boundary conditions, this integral can get kind of ugly, right? So we already talked about method of images. That's what we went over last time. And the important thing about method of images was this idea that we can replace a complicated problem with a simpler one. As long as the boundary conditions are exactly the same. And so really when it comes to finding solutions to the differential form, because remember our goal here was to deal with Laplace's equation. And that's this del squared V equals 0. Our goal was that as long as we can find a solution, there's only one solution, and that was that uniqueness theorem that we talked about. So if we can find one solution, that's the only solution there is. And so if there's a different problem that has the same boundary conditions, if you can get that answer, then that's sort of automatically your answer. So you may as well use the simpler problem where you just have point charges and things like that. And so that's sort of one way to kind of take this direct integration. We're turning it into a differential equation because we have this, this del squared going on here. But because of the kind of the properties of this equation, this uniqueness theorem thing, we can kind of do some tricks to make it actually easier than doing a big ugly integral. And so we're going to basically do the exact same thing today with a kind of a different move, where we are going to solve this differential equation directly, but we're going to make some assumptions that will make things a little bit easier. And the technique is called separation of variables. Ugh. And the idea is that we're just going to solve for V as a function of, say, x, y, and z, or r, theta, phi, whatever coordinate system is convenient for the problem we're talking about, but we're going to solve for this directly from the Laplace equation. Let me get this on my way. And so let's kind of think about what that means. So how are we gonna start that? The idea is that when we have a problem, we know the boundary conditions. Right, and so that means if I have, if maybe I have like a box, and I know what the potential is at the top, the bottom, the left, the right, that kind of thing. So I know what the potential must be, and we would like to know, we need V sort of inside the boundaries. Right? And so what we're going to do is go right to Laplace's equation. And for now, let's deal with things in 2 dimensions. So we're going to use Laplace in 2D. And so when we're talking about del squared, this differential equation del squared V equals 0 in 2 dimensions in Cartesian coordinates. So I'm going to just be basically using X and Y here. That's going to turn into the second derivative of V, second partial derivative of V with respect to X, plus the second partial derivative of V with respect to Y is equal to 0. So this is the equation that we have to solve. We want to find V of xy that gives us 0 when we add these 2 second derivatives together. And not only that, we needed to also match the boundary conditions that we come up with.